All right. So welcome, folks. Welcome to week 5 of Qubit by Qubit. This week, we're going to talk about measurement in Qiskit. I'll go ahead and share my screen so we can walk through this together. So what will measurement in Qiskit look like? Well, we'll approach this in a few different steps. First of all, we'll take a moment to review what we've seen so far, these 3 steps of coding up quantum circuits, as well as review using multiple gates, since that came towards the end and that may feel a little more challenging. Once we've gone through the review of what we did last week, we will also introduce measurements into the mix. So we'll see what changes in what we've done. The short answer is not much, so hopefully it won't be too challenging, but it's still some new syntax, and we will actually implement this. So you'll make measurements using a simulator today, and then we'll talk a little bit about how you interpret the result of this, in particular, something known as a histogram. Now, before continuing, I would just say I'd love for you to turn your cameras on so that we can all see each other's lovely faces and engage. If you're not able to, of course, that's fine. Love to see a virtual background or a picture of you. And yeah, just be able to see everyone's face. All right. So some general announcements. There is a homework review on Fridays from 4:30 to 5:30 p.m. Eastern Standard Time, wherever that is in your time zone. This is a great chance towards the end of the week to just take a look at the homework. Maybe you've tried it before, but you have a few questions you're stuck on, or things you're curious about with the homework. This is a great chance to get some help with it and to review it. There are also general office hours, so it can be about homework, but it can be about anything else with the course on Thursdays from 9 to 10 p.m. and Sundays 11 to 12 p.m. Again, all of these times are Eastern Standard Time in the US, so do make sure to double check what that is for you all. We also really love to know how you're doing with the materials. We want to be putting out things that are really helping you as best as possible, and one way to do that is to get your feedback. So we'd love for you to let us know how you're doing in the lab and the homework this week. There'll be some opportunities to directly express that. We'll be putting out polls throughout different times of the week. But yeah, please be open and honest. Tell us everything, all the good stuff, all the other stuff, just everything, so we can keep improving and making this as awesome as possible. If you haven't joined the Discord server already, I know there's a lot of people that have, but if you haven't already, go ahead and join. It's a great space to just talk with people, to ask questions, particularly as we're exploring some of these kind of wilder concepts and we start looking into all these things. It can be really nice to kind of talk with the community of you all and all of us. We really are creating a community here, and it's nice to engage with that if you have the time, instead of just focusing on the academics. Of course, the point here is also that this is an easy way to do this that hopefully doesn't take up too much time, as I know we're all pretty busy. Lastly, if you have any questions about Canvas or issues with your sections or anything like that, you should email student@qubitbyqubit.org. This is the best place to go. We really are not able to monitor our inboxes on Canvas very much, or at least not at the rate that we get things. This is a great one place to send things, as well as the help form on Canvas. Okay. Lastly, some logistics. The attendance code for the week, 8301. I believe the quiz should be up. I will also put this in the chat so you can look at it later, but go ahead and take a moment to enter this now. So this is the attendance code for this week, 8301. Go ahead and enter that now. If you go on and notice it's not on there, please do let me know. But I'll give everyone a minute or so and I'll leave this slide up to do that, as well as to ask any questions about anything we've discussed so far. So let me know if you have any questions. go ahead and fill out the attendance poll on Canvas. And otherwise, give me a thumbs up when you've done this. Thumbs up if you have entered the attendance poll. Awesome, I see someone did, so should be up.
I have a problem with opening the notebook. I can't open it.
Okay, is this, did you download it from Canvas or from the chat?
I downloaded it from chat, and in Jupyter or QxQ, I just downloaded there, but when I open it, I just saw some numbers on the screen.
Interesting. Is this an issue you've had before, or is this a new issue? Just curious.
It was like that in first week, but then I solved it. But also the last week and this week, I can't open it.
Okay, I just want to see if it's something specific to this notebook or if it's a general problem. So it seems like it might be a general problem. One thing I'll suggest is to make sure to rename, or make sure that the ending of it is correct, and make sure that, yes, as Wayne points out, make sure that you're also on the correct website. So yeah, just confirming you're not on Google Colab or anything like that. It's on the IQX link that was just sent in the chat.
Okay, I will try again. Thank you.
Okay, yeah. Yeah, I know that there can be some frustrating problems with getting set up with all this, so please do let us know what if you're having any problems. We want to make sure that you're all getting experience with this and you're getting hands-on. But do know that no matter what, all the materials are there for you. So if you ever have an issue on a given day, you can always follow along and work with us and still enter your answers in the chat. And you'll still get all the confirmation of what works and what doesn't. Okay, so let's start. Let's dive in. First of all, let's review some of the stuff we've seen so far in QxQ. This is a lot of new stuff, so I want to make sure we're moving through this at a pace that's working for people. First, I want to review the steps we talked about, the 3 steps to creating circuits in QxQ. These are really the core steps. These will not change throughout the year. Everything can be broken down in these 3 steps. The first one is to create an empty circuit. We're actually going to see some ways that we change this today, but generally, you create an empty circuit just like this. You tell the computer, hey, I want a quantum circuit, hence the name, right? Quantum circuit. You say how many qubits you want in your circuit, and then you store the result in a variable. So we have a variable here. We typically use lowercase qc for quantum circuit, but you could name this anything. You could name it Bob or Alice if you wanted. Then, once you've created the circuit, you've kind of set up your landscape, you can now start to fill it. So you can add gates to the circuit, where you can call from the circuit, we called it QC, dot whatever gate you want, X, or as we saw, this can also be H, the Hadamard gate that we've seen, and then whatever qubit you want to apply it to. So far, we've only seen single qubit circuits, so this will always be 0. Lastly, we want to actually do something with the circuit. So we can draw the circuit, or we can visualize what will happen with the circuit. Today, we're actually going to see a 3rd option for this step, and throughout the year, we'll end up seeing a lot of options, because depending on what you want to do, you may want different results here. Usually creating the circuit and filling it with gates is going to be roughly the same, but there's a lot of different ways you might want to analyze what that circuit does. So here's 2 tools we've already seen. We're going to get another one today and more to come. Now we can also add multiple gates. We are not restricted to just one gate at a time. And here's how you can do it, where each of these steps is a different line of code. So first you create your empty circuit. Then, and on the right, we see drawings of what we'd get. Then you can add, say, an X gate. So we have a single X gate here. Then we can add another X gate. So you add gates one at a time. But notice that now these 2 X gates have added together. So we now have an X and then another X. And then we could add something else, an H gate, say, an H gate right here. So if we want this circuit in the end, we basically need to do it one step at a time. First the X, then another X, and then the H. Okay. So what I'd like to do now is, before moving on, I just want to check in if we have questions on what I've thrown out so far. So this is a review, but I'm moving quickly. So I want to see, do we have questions about any of this? Okay. I see someone's let me know about some questions that are kind of specifically to last lab. I don't have the numbers memorized, so I'm just not sure exactly what those topics were, but if you could let me know what the content of them was, or if there was something particularly about them that you were confused about, I would love to help you out, as I'm sure you're not the only one who's wondering some things. So I'll keep an eye on the chat for that. But otherwise we can move on. Another point that we will continue to see is that order matters. It really matters what order you apply these gates in. Applying an H and then an X gate is absolutely not the same as applying an X and an H. There are very rare cases where we can switch them and it's fine, but that is a very rare thing. And this is not just some weird thing with H's and X's. This is general, and this actually comes from some very deep quantum mechanics. We're not going to dive into this now, but just as a little kind of FYI, this actually has to do with Heisenberg's uncertainty principle, if you've heard of that. We will likely explore that in semester 2 when we really dig into these matrices in this math. Okay. Okay, so someone let me know that the questions they had was about preparing a qubit in a certain state and then applying a gate to it. We can discuss that today. I think it'll be easiest to see that in practice. So why don't I point out some ways we can do that today, and then let me know later on if you feel like you're still not sure about it. I'm sure you're not the only one. So I'll make sure to point out specific cases of your question to hopefully clarify it. Okay, so this was a review. I want to get in and practice. That's really the best way to learn this, is just doing it, just practicing it, doing it over and over again. So what I would love is for us all to go to this link, to the IBM Quantum Experience, and to start coding. So go to this link. I will send it in the chat as well so that everyone definitely has it. Some folks want to review last week's questions as well. Yeah, you're not the only one to express that. Yeah, you know what? I think it'll be valuable to go over those. Let's go through the review from this week first, because this is about reviewing concepts from last week. And then once we're done with this review, I would be glad to take a moment to go over some of the specific questions we have from last week, if they're still around. So make sure you're on IQX and you've got your notebook open. Should look something like this. Go ahead and just give me your thumbs up if you've got this open. It's all working. Just want to make sure I'm not running too far ahead here. Beautiful. Okay. It's all right if you're still taking a moment to open it up, but I'm seeing a lot of thumbs up. So let's dive in. First of all, part 0. This is a part you will just see all the time. We're always going to provide it for you. It's really not an important skill that you remember all these exact lines. Go ahead and just run this. It's always important, just run this cell beforehand and make sure it prints out libraries imported successfully. Again, that's just importing all those libraries, all those functions in particular that we want to use. Awesome. Okay, so make sure you run this first. Oftentimes, if you have an issue, it's because you just forgot to run that. And trust me, it happens to us all. We just assume it's already run and we go on. Now let's dive in here. We're going to do the first 3 exercises together, as in I'll do them up here on my screen, but I'd love for you to follow along yourself to give this a guess and see how it compares. So exercise 1, let's create and draw a 1 qubit circuit with 1 X gate. So we're really kind of diving in here to the things that we saw last week. Because this is the first exercise, I'll go ahead and just do it for us. So QC equals quantum circuit of 1. That's saying it's a 1 qubit circuit. It is an empty 1 qubit circuit so far. Then I want to apply an X gate. So QC.X, make sure you do lowercase x. It's convention that when you write the gates, you use uppercase, but in code, we use lowercase. Personally, I know that always tricks me up. So if you ever have issues running gates, double check that you did lowercase. Then we want to apply this to the 0 qubit. And then we're asked to draw it. So it's 3 steps in action here. Step 1, create an empty circuit with 1 qubit. Step 2, apply an X gate to the 0th qubit. Again, we're indexing by 0, just a computer science convention. And then lastly, we want to draw it. Let's see this beautiful circuit. And then we can run, and voila. We have our circuit right here. Q representing our single qubit, and X representing the gate that we want to apply. Okay. Yes, someone is asking. Yeah, a couple folks are asking about sharing the link. I believe it should be on Canvas as well. Let me take a moment to open that as well. While we're doing this, let me know if you have any questions about what I've put down so far, or if this looks good. Actually, I'll share this. So just in case anyone's having trouble finding the links and everything, I believe you should be able to find everything you need on Canvas. So I'll walk through this with us all. So you go on Canvas, should recognize this page. And then if you go to modules, you should really see pretty much everything you need. I believe this is where we can find what we want. In particular today, we want this. So we're in week 5 right now. We want the student notebook that says download for lab. So that is here. I will send a link to this page. You will have to sign into Canvas to get that, but I just want to send that so that you can all find the right link. Okay. Jumping back here. Let's now go into exercise 2. Together, let's create and run a 1 qubit circuit with 1 H gate using visualized transition. So again, we're creating a 1 qubit circuit. Looks like this, create an empty circuit with 1 qubit. We want to apply an H gate. So we apply that to the 0th qubit. And then now instead of draw, we do the visualize transition function, where we supply the quantum circuit that we want to visualize first. And then we can set this parameter trace equals true, which just says, I want to actually see what comes out. Now, this can take a little while. There are actually ways to adjust this. Another TA actually pointed this out. There's some ways to make this a little faster. For now, I'm not too concerned, so I'll run it. But as we move on in the future, we will likely end up doing this a little faster. Okay. Now let's look at exercise 3. Let's create and draw a 1 qubit circuit with 1 X gate applied first and then 1 H gate. So now it's getting a little trickier. We're applying multiple gates. The start is the same. There is no difference here. QC equals quantum circuit of 1. We're just creating a single qubit circuit. And then I want to apply, oh, there we go, that ran. We'll look at that in a second. Then I want to apply an X gate. Same thing as it would have been so far. The difference with applying multiple gates is that before I draw it or run it or do whatever I want, I still need to stay in step 2 and basically just apply whatever other gates I want. So for instance, like this. and then QC.draw in this case. And now you can see we have multiple gates here, the X applied first and the H applied second. So multiple gates are really just one gate after another. And this is the same in the circuit as it is in the code. You apply one gate on one line, the next gate on the next line. And if we wanted more gates, we could go on from there. Okay. Now, I'd love for you to go through exercises 4 through 6, as well as to ask any questions that you have. So I'll take this time to let you go through exercises 4 through 6, and I'll answer any questions. Yes, please.
So actually, when I did the third one myself, it's showing some error, even though I did the same thing.
This third exercise here with the X and H. Okay.
No, actually that's visualize transition one.
This one.
Yeah, sorry, second.
Yeah. So let's take a look at this. So first of all, double check that your code matches up. It's important. One strange thing with visualize transition is we do not call QC dot visualize transition like we do with most other things. We pass QC in as the first argument, which is just fancy words for saying QC goes right here instead of out front. If you run this and it runs successfully, you should get this out and be able to see this circuit, which again rotates our 0 state down here to the plus state along the x-axis. Now, if your code is just not compiling, it's just not running.
Yeah, I'll do it again, and if I face the similar problem.
Beautiful. Okay, wonderful. Yeah, do we have any other questions about these exercises, or how are we doing? Okay, so again, give everyone a moment to run through these. Give me a thumbs up when you're done, and feel free to ask any questions along the way. Okay, and let's see. I think I see a couple people, including Gemma, looks like having some issues with the notebook. Have people figured this out? I accidentally shared the solutions, did I? Thank you for pointing that out. Yeah. Still valuable for you all to go through and do them yourselves. The link I shared was, thank you for pointing that out. Oh, yes, I see. Okay. Okay. Yeah, I accidentally shared the solutions. Again, this is not a graded exercise. It's just for you to go through. So it's not bad to have them. We'll share them eventually, and I guess you get a sneak peek. But for now, try to focus on just doing these. Thank you for pointing that out. Okay, let's go through these. Exercise 4. I would love for someone to share their code. Yeah, who wants to share their code? You can send it in the chat if you would like. Just copy and paste it in. It may not look too pretty when you do it, but let's just share, and as many folks as want to can share. That doesn't have to be one person. But exercise 4 here in part 1. Awesome. Okay. Nice. Nice. Yeah, okay. So for exercise 4, I'm seeing a lot of little differences, but the general structure is the same. So I'll show you how I would do this. Circuit 1 QC.x of 0, QC.h of 0. And then note that for exercise 4, we're looking to use visualize transition, not the draw function. Honestly, it's far more important to me that you get the first 2 steps. Those are the more general ones, but it's still good practice to get used to this. Now I'm going to add a little extra piece here that you don't have to, but it'll just speed things up for us. Okay. And in the end, you should get something like this. Now I've added a little extra parameter that we'll talk about a little bit next week, probably. That just makes it a little faster to load. But you should get something like this, although you probably got a nice smooth path instead of this kind of dot. Okay. Again, the general structure should look the same. The X and the H, note that it is not the same as applying QC.H and then QC.X. Now, I noticed some people had different spacing. You know, some people like to have something like this, or to name their variables different. I noticed a K in there. These are all totally fine. The most important thing, the most important guiding principle is clarity. When you're writing your code, think about what it would look like to someone else who has no idea what code you're writing, and you want to try to make it as clear as possible. Okay, as clear as possible. Oh no, no worries, Ellen. Okay, so I will also point out in this case an answer to a couple people's questions about preparing states and then applying gates. The honest truth is, preparing a state, as in I want to prepare my circuit in the 1 state instead of the 0 state, is the same as applying a gate. Because if we really break this circuit down, and I want to see if I can zoom in so we can really see that. Thank you for pointing out. This one's actually asking about applying H first. The conversation can still hold with that though. Thank you for pointing that out. Yeah, Mohammed, thank you. So we apply an H and then an X. We can actually view this as preparing our qubit in the plus state, right? As in, our qubits always start at 0 in Qiskit. But then we can imagine that this first gate we apply .h, well, that takes us to the plus state, right? In the kind of animation here, and I'll zoom out, it brings us down to the plus state here along the X direction, the X axis, and then we apply an X gate. This is the same as if we say we're preparing a 0 and applying these 2 gates, or we're preparing our qubit in the plus state, and then we apply some gates, particularly the X. So saying that we're preparing in 1 state versus applying these 2 gates, it's really just a matter of interpretation. The quantum circuit itself doesn't actually change. So in some sense, it's almost a trick question. Seems like I was able to answer some questions there, I'm glad. But yeah, really the point is, preparing a state is just a fancy way of talking about applying a gate to get you into that state. And the honest truth is, this is what people do in practice with a real physical quantum computer. If you have a circuit where you want to prepare all your qubits in the plus states, this is what you do. You apply Hadamard's, real physical Hadamard's. We'll see more of what that actually means in practice down the road. Qiskit also does provide some different ways to do this, but really this is the most reflective of what people do in practice. So I think it's the most valuable to see. Okay. People are having a little trouble visualizing. Visualize transition can be a little funny, which is why we don't use it too much. It's very helpful to see some of this, but it's long-term, we'll be using a lot of other things. So if you're having issues with it, then I wouldn't worry too much, so long as the drawing works. That's more important to me. Okay, exercise 5, create a 1 qubit circuit. Ooh, wow, that's all right. Quantum circuits. This is what happens when you have too much coffee. And then with an X gate, and then 3 H gates. So we have 3 H gates. I like to just copy and paste, although it's important to keep track of it. I'm going to use a space here, an empty line, just to make sure I did this right. So 1 X gate, 3 H gates, and then we draw. So now we have this complicated 4 gate circuit, but really it's just 4 lines and we can try. Notice that nothing changes here except this middle part, step 2. Okay, lastly, create a 1 qubit circuit and then apply those gates.
Excuse
So
me.
it's, yes, please. What's your question?
So actually I'm doing the code right, but still I'm not able to visualize or even draw. Like my image is not showing like yours.
Ah, I see. And you're in the IBM Quantum Lab, the IBM Quantum Experience.
Yes, sir. Yes,
Okay.
sir.
My first suggestion would be to rerun part 0. That's where we're getting the functions to be able to visualize. So I would suggest rerunning that and then going to try to run your code again. Yeah.
Okay, thank you, sir.
Did that work? Okay, wonderful. Okay, so we apply an
Yes,
X.
yes, I got it. Thank
Beautiful, beautiful. Glad to hear it. Yeah. H and then this. So notice, I mean, it's hard to keep track of these gates, and you'll notice this a lot. Generally, what I like to do is I like to break it up in a few sections that are a little more readable. So I'll say, okay, let me just look at 2 gates at a time. Or in the future with different algorithms, there'll be kind of some logic behind why we apply some gates versus others. And so you'll have natural ways to break it. But here, at least I can double check, because seeing all those lines at once can be really confusing and hard to keep track of. So I believe it's XH, XX, HX. Perfect. And then QC.draw. Again, a very complex circuit. It would take a little while for us to like really analyze what this is doing. But hey, as far as the coding goes, basically it's just copy and pasting more lines, just writing more of the same lines, right? And that's the beauty of Qiskit, is we can really write and draw things like this pretty easily, even if understanding what they're doing is a little more complicated. Any questions on part 1? Part 1.
So may I ask a question?
Yeah, please.
Can in exercise yes 5, can we do something like loop the H gate?
Yes.
I mean,
Yes.
do we have to write all the gates one by one?
No.
Or do we have another chance?
Yeah, this is a great question. So we have not looked at loops in Python with everybody. So for that reason, I'm writing it all out. If you are familiar with loops, you absolutely can use them. So you could reduce this to just a couple lines with loops. We'll look at loops down the road. For now, it's not necessary, but yes, no, you can absolutely do it. Okay. So let's move on.
Doubt.
Yes, please.
So the complicated gates that we just made,
Yes.
probably in exercise number 4.
Yes.
Exercise number 4 or 5. So I just, for the fun of it, tried to visualize transition it to see where it would lead us, and it has left me slightly curious, because applying the Hadamard gate 3 times on a +1 state somehow still gives you -1 state.
Yeah.
It's kind of amusing how that happens.
So we're actually going to spend a lot of time answering questions like that. In other words, is there any way I can predict what this circuit will do? right? So that I don't have to code it up and just see, although that is very scientific. Can I predict what this will do? Can I know what state I'm going to get out? And can I explain why? It does turn out that there's some rules to tell you why you would get a, I believe, a minus state out of this. For now, I want to focus on just being able to measure, and really measurement is the key to being able to answer some of these questions. So we can really truly understand what these do. However, as the semester goes on and really the year goes on, we're going to see some increasingly sophisticated tools for answering questions like that. But these are great questions to be asking, and I would encourage you and everyone to keep kind of exploring these things. And that's part of why the visualize transition function is nice, is to be able to explore this and see what ends up happening. Okay, so let's now move on to measurement. So this is the new stuff for today. So there are really just two things that change, and we're going to look at each of these individually, but first I'll just summarize. First, we need to include a classical bit to store the measurement result. When we do this at the very first step when we create the circuit. So if you remember from lecture, in order to be able to do something with a measurement result, we need to store it somewhere. It is fundamentally a classical piece of information we get, so we store that in a classical bit. Then later on, once we've applied all our gates, we can go ahead and do this storage. We make a measurement. There's a QxQ command for this. We make a measurement and we store it in that classical bit. So let's see how this works. First, we just slightly change our very first line. We still have QC equals quantum circuit the same. The first argument is the exact same as it was, the number of qubits. But now we can add this extra parameter, this extra piece here that says the number of classical bits in your circuit. So you can include this or not, but if you want any classical circuits, then you can get this out. It's worth noting that basically what we've been doing is just 1, 0 so far. We haven't had any classical circuits, and you can, or classical bits, and you can run it that way too. That's fine. But if you're just going to have qubits, you might as well just do 1. So we have 1, 1, which is 1 qubit and 1 classical bit. Then later on, after we've applied all our gates, so later on in the circuit, after we've applied all the gates we want to, we can make a measurement. This consists of 2 parts. The first one is which qubit you want to measure. So this is saying qubit 0 is what I want to measure now. I want to measure the state of qubit 0. The second number here is which classical bit you want to store that result in. So the first one is quantum bits, the second one is classical bits. The ordering is very similar to when we made the quantum circuit. Qubits first, classical bits second. This is the index of the classical bit. So we store the result of measuring the 0th qubit in the 0th classical bit. So there's no better way to learn this than by practicing. Let's take a look. So we're moving on to measurement in part 2 here. So let's follow along with a few exercises to see these together. So I'm going to walk us through it, but please ask questions as we go, and hopefully it'll start to become a bit clear. So for exercise 1, we want to create and draw an empty quantum circuit with 1 qubit and 1 classical bit. So it's going to start very similarly, but now we have 1 quantum bit, just like we had before, and 1 classical bit. Then I go ahead and I draw my circuit. And there you go. So notice it looks the same at first, just like the code does. But now we have this extra piece down here, C. So Q for qubit, C for classical bit. We don't have to worry about this -1 right now. That's basically just saying we have 1 classical bit. But note, the big thing to notice is we have a C for classical bit, and we denote the difference between them with 2 lines for a classical bit. That's standard across the quantum computing community. We use 2 lines to denote a classical bit and 1 line to denote a quantum bit. There's no real deep reason for that. It is just convention. Okay. Any questions so far?
Yes, why is there a
Please.
small 1 over it? Over C.
So
class?
Yes, so that's just saying we have one classical bit. It's obvious to us from the code what is happening, but in this case, it may not be obvious if you just saw this drawing. Because we're only dealing with single bits this week, this doesn't really mean very much for us, but in the future, we will have more classical and quantum bits, and so it'll become important to keep count of them. So this will become handier later on. For right now, we don't need to worry about it. Yeah, good question.
So, sir, why is there a slash between the two lines?
That's another thing relating to the count of classical bits. Again, because there's only one, it's not really clear why this helps. So I'll say, let's kind of put a pin in that. We can discuss it when we start looking at more, which will be as soon as next week. And we'll actually see why that is. But basically, it's shorthand for just saying you're including a bunch of classical bits in one. But in this case, our bunch is just one classical bit. So again, that will become clear as we go. The most important part here is that to create this circuit, we just add an extra piece here, comma 1, and we can see that we get a C bit out, classical bit.
And what is going to happen if we write 2,1? Then it will be 2 qubits?
Yes, exactly. So if we wrote 2,1 here, we would get 2 qubits. We're going to explore that soon. Next week, so I'll leave that for now, but yes, and I would encourage you all to play with that. Like, these kinds of questions are great, and I encourage you to play around and change these numbers, see what works, see what doesn't. The best programmers are the ones that just kind of basically try to adjust the code as much as possible, play with it, break it, do what you can. But okay, for now, let's see this. Exercise 2. Now we want to create an empty quantum circuit with 1 qubit and 1 classical bit that we're going to end up drawing. So note that I've just copied and pasted my code in. This is super standard stuff. I encourage you to write it every single time when you're first starting, just to get the muscle memory to learn. But at some point, it'll just become so natural that you can just copy and paste like this. Now, we want to measure the qubit state and store the result in our classical bit. So we put this piece here. I tell my quantum circuit I want to measure. So I call the measure function. It's almost like calling a gate, X or H, but now we're saying we want to measure. We don't want to apply a gate. Then we need to specify which qubit we want to measure. In this case, we only have 1, the 0th. And then we specify which classical bit we want to store that in. We also only have 1, the 0th. So we have this. Now we draw the circuit, and here we go. So now we see we have a similar circuit to above, but now we have this measurement here. So this is the symbol that Qiskit is using to show that we're measuring. There's a lot of variety in the symbols that people use for measurement, but generally it looks something like this, like some sort of dial or something like that. Okay, and what this is saying is we've measured the 0 qubit out here on our 1 classical bit. Okay. Lastly, we want to do the same, but now we also want to apply a gate. Let's actually make this an interesting circuit. So quantum circuit of 1, 1. Now we have to apply the X first, and this is an important thing. We have to, the order here matters, just like with any gates. So we apply our X gate, and then we measure. So we measure the 0th qubit, and then we store that in the 0th classical bit. And then let's draw this out. And we should get something like this, where we apply the X gate first, and then we measure. So make sure you're getting the X gate first and then measuring, not the other way around. Again, we read left to right. So you can see here, we still have this 0 here because that's just saying, reminding us we're measuring the 0th qubit. That is not saying we get the 0 state out. In fact, if you analyze the circuit, you'd see that would not be correct. So this is the 0th qubit. That's what this notation is saying. Okay, any questions on this? I've thrown a lot at you. How are we feeling about this? Any questions?
And just for the fun of it, I tried to draw the circuit first and measure it later on, other than the other way around, and it just gave me a simple line of code like the instruction at IBM Quantum Lake. It just gave me a sort of a string of code, and I couldn't make out of that.
Interesting. Yeah, if you draw, after you call draw, it'll just print, or it'll just draw what you have. And then if you run any commands after that, that will not be drawn. And based on how these work, you may end up not seeing anything that's particularly meaningful. So it's important that the last thing you do is you draw, and everything else is included in here. You can switch around the order of all these things, although for this exercise, it's important X comes first. But generally, you can draw, or you can do whatever you want until you draw. Okay, I'm glad to answer more questions, but I'll say go ahead and work on exercises 4 and 5, applying this, and I'll leave this part up of, or this part of my screen up so you can refer back to it if you get stuck. But go ahead and work on exercises 4 and 5. I'll give you a couple minutes to do that and answer any questions. Yes, so someone was asking the left versus the right. So it's actually, yeah, it's the other way around. So this bit here, this first one on the left is the Q bit, and the second one is the classical bit. So qubits always come first in Qiskit. Qubits always come first. We're doing quantum computation, qubits come first. If we're doing anything with classical bits, they always come second on the right. Yes, yeah, Ricardo, I see. Yes, exactly. This 0 down here by the measurement symbol is just saying it's the 0 measure, or the 0 bit qubit being measured. So this line here, QC.measure, let me zoom in so we can see it a little better. We can really break this down as this part that I'm highlighting is saying the qubit we're measuring. This is the index of the qubit. Now we only have one, so it'll just be 0 for us all day long. We're measuring the 0th qubit. This says where we're storing the result. Classical or quantum measurements always give classical results. This is a strange part of it, but basically we need to know, are we in the 0 or the 1 state? Those are the only options we get for measurement, as we saw in lecture this week. So we need someplace classical to store that information. That's what we're doing here. We're creating a classical bit to store the result of our measurement. The classical bit is basically like a notepad where we write down the result that we get. We need to specify to IQX, to Qiskit, where do you want to write down the result you get? So this is saying measure qubit 0 and write the result down in classical bit 1. For now, it'll always be QC.measure of 0, 0. This line will never change this week. Starting next week, we'll actually see it change a little bit. And I actually think at that point, this will start to make more sense because we'll have more than just the 0 qubits and classical bit to measure to. Okay.
So
And
why
yeah,
is there a small 0 below the measuring dial in the drawing?
great question. So yes, this small 0 is just saying the index of the qubit you measured. So this is saying we measured qubit 0 and stored the result on this classical bit. Again, the idea is that if you had no access to the code and just this circuit, we would want to understand everything. So this just makes it abundantly clear. Yeah, just answering a question in the chat, 2 H's do revert back to the original position. We will see why later on. It's a great question though. And we can prove that that's the case, but later on. So let's go through these, and I want to make sure we get to the last bit here because that's the really exciting part, I would say. So exercise 4, create a 1 qubit, 1 classical bit circuit. So it looks like this: 1 qubit, that's the first part, 1 classical bit, that's the second part. We want to apply an H gate to the qubit, and then we want to measure. Again, for us this week, it's always going to be 0, 0. And then we want to draw that circuit. And we should get something like this out. Note that it's very similar to above, but we just have a different gate. Instead of X, we're applying an H. Awesome. And here we're getting even more complicated, multiple gates, measurements, things like that. So QC dot, we apply 2 H's, and then we apply an X, and then we measure, and we draw. There's a lot going on here. It's okay if you're feeling a little unsure of what's going on. You'll get plenty more practice with this. The solutions will be posted. I'm glad to answer questions, but basically we'll get more time with this. Okay. Now I want to move on to the next part where we'll still practice this, but we'll be able to actually see the results. So very quickly, I'll just say, we actually want to see the results, right? This is great and all. We can set up these circuits, but the whole point of measurement is that we can actually know what's going on. Now, we will be able to actually run this on a real quantum computer down the road, hopefully in the next few weeks, really. But to get started, to get these results faster, we're going to use a simulator that Qiskit provides. This is known as the QASM simulator. It actually has a lot of them, but this is a really helpful one. I believe it stands for Quantum Assembly Machine. Could be wrong on that. It was hard to find, actually. And this is a new way to do step 3. We're going to provide the code for you to do this. You are not responsible for knowing this. We will always provide the code for this for now. The important part is knowing what comes out of this. So let's actually just jump right in. There's no syntax you have to learn here. Let's actually see this in action. So we're going to part 3. This part, actually, exercise 1, we've just provided you the circuit. So we just want to simulate this and just see what comes out. So notice that the first 2 parts are the same. QC equals quantum circuit of 1, 1, QC dot measure 0, 0. Same as what you're doing. But now part 3 is a little more complicated. This is the code that you do not have to memorize. You do not need to understand for now. I'd be glad to break it apart later. But for now, just run it and you should get out a result like this. Okay. Okay. So what do we think we're getting here? What does this mean? Sorry, I think I heard someone talking, but it was a little low volume. Could you possibly repeat that?
Probability of finding the qubit and state 0 is 1.
Yeah.
Like,
yeah. Graph of some kind of experiment on a quantum computer. Yeah, totally. Love that, Giga. Yeah. So this is graphing the results of running our experiment. Now, this is a simulator, but it is accurate. And so what we get out is what is called a histogram, something we're going to become more familiar with time, where the 0 state is measured 100% of the time. That's what this says. The probability of it is 1. Probabilities are measured from 0 to 1, as this graph shows, 0 to 1. 1 is the highest. That means every single time you get the 0 state out. That should also make sense based on what we've learned, because we prepare an empty circuit where we know that qubits always are set to the 0 state, and then we immediately measure that qubit. Okay, let's see some more examples. So we now want to apply a 1 H-gate measure. Now notice this circuit has an X in it, so it's a little trick to throw you off. We want to make sure we're applying an H-gate, make sure you're really reading the code you're getting. Okay. Now, what do we think is going to happen? Before I show the results, we apply an H-gate. What do we think is going to happen here?
The results will be split up, roughly 50-50.
Yeah, the results will be split up 50-50. Yeah, let's take a look. Exactly. We get a 50-50 split here, right? exactly like we predicted, 50-50 split. Just for the fun of it, just gonna run it again. Notice I ran it again and I got a slightly different result here. Before I got 0.5 every single time, I will say that was actually extremely coincidental and lucky. Why do we get this? Oh yeah, because it's random. Yeah, quantum measurements are random. It is not guaranteed that you get a perfect 50-50 split every single time. Just like if you flip a coin, it is not guaranteed that you get head and tails exactly 50% of the time. You might get it close, but it might not be exactly. It's the same thing with this. We set up a superposition using H, then we measure. So we set up H and then we measure. And in this case, I got 51.3% of the time. That's how we can interpret this. We got a 0, and 48.7, we got 1. Note that they're really close to 50%. They're just not quite there. Okay. So it's always important when you're running code like this to run it several times, because every single time you'll probably get a slightly different result out. Notice that the numbers change every single time I run it. Sometimes you'll get similar results, overlapping results, but if you run it enough times, you'll see a lot of differences. Okay.
And why we have 50-50 in the first one?
Ooh, to be honest, that was just extremely lucky. There's nothing deep about that. There was nothing, I honestly was shocked a little bit when I saw that. It is extremely rare that you happen to get a perfect 50-50 split. So the reality is that every single time you run this, you should get a different result out. In fact, if you are running this, your results are probably different. Now, I want to make sure everyone is getting this graph out, but if the values are different, these numbers, that is okay. Okay. Now, we are at time, so I will stick around with questions, and I'd encourage you to go through the next few exercises. But at this point, you've seen everything that I want to make sure we got to today. In particular, you set up your quantum circuit with a qubit and a classical bit to store the measurement. You apply your gates just like we've seen before. Then you measure and store the result in a classical bit. And then you run this code. And again, you are not responsible for this code. So please focus on understanding the results here. It's far more important you understand this than that you understand what this code is doing. We'll have time to go through that later. And if you have time, go through the rest of these exercises. You'll also have more practice on the homework. Okay, so I'll gladly answer any questions, but otherwise you are free to go. Please do make sure you enter the attendance poll and get your deserved credit for attending today. And it was lovely to see your all's faces today. Okay, so again, attendance code was 8301, as someone pointed out.
So
Have a lovely day, folks. And yeah, I'll answer any questions. How's it going?
I'm
What's the
getting
question?
a similar result for every code. Is it also random or is there a problem?
That's interesting. So you run it and you get the exact same thing every single time?
Yeah, for every code, first, second, third, and fourth.
Oh, interesting. Yeah, maybe you're just very lucky today. You know, maybe today's your day. Just the gods are in your favor. I don't know.
Maybe.
Yeah, that is interesting. If you're getting out the histogram, that picture that we were getting, then your code is running correctly. You're just, it's getting very lucky, I guess. Yeah, any other questions?
So in the code, there was
Yeah.
a number in the QxQ code, shots equal to 1024. Like
Yes.
that's 2 to the power 10. So is there any correlation with this number and the number of times we're doing it?
Yes.
Like,
So
is this number necessary somehow?
yes, that's a great question. So this is something we'll dive into more. Again, for now, we don't have to worry, but yes, basically shots is one way of saying how many times we make a measurement. It's kind of experimental physics talk for that. So basically we run this, although experimental physicists would not like that I'm calling a simulation an experiment, but shots basically says how many results we're looking at. So that says 1,024 results. You can play with that number if you'd like, but for now we preset it just so that it was a high enough number that you could get some interesting results. Yeah.
I had a quick
Yeah,
question.
Yeah, please.
So I jumped to exercise 6 and Nalan asked us
Yeah.
to create 2 H-gates and then measure it. I was just
Yeah.
confused as to how it's 100% chance that it's 0, it's in the 0 state because the probability is 1.
Mm-hmm. Yeah. Yeah, this is a great question. So the point of this is actually so that you maybe notice this, and it's really valuable to kind of go through and notice that that is an interesting result, right? You apply one H-gate and you create a superposition and you get out this roughly 50-50 split, and then suddenly you apply another H and that goes away. You get out the same state every single time. I'm just going to say for now, I'll leave that as a cliffhanger, but we will actually learn how to understand why that is. And I will tell you, you're getting the right result out with that. So at the very least, I'll confirm that is what we would expect. Why is something we'll dig into a little bit as we really explore the properties of these different gates. There's a lot of very rich physics in these.
Okay, thank you so much.
Okay. So with that, I will call it a day. Have a lovely week, everybody. Go around and make some quantum measurements, and I'll see you all next week.
And may I say something? Could you please send me the notebook in mail or in chat again, because I can't open it. I don't know why, but I couldn't.
Sure. I'll also say, I'll include it here. I'll also say, I think if you're having this issue multiple times, it would be valuable to reach out to the student help email so that they can really help you get set up. I will send that in the link as well in the chat. Where is that? Here we go. Yeah, go ahead and email this email, which is there to help, and they should be able to help you get set up. I want to make sure that you don't run into this issue over and over again, and you're able to just kind of run smoothly. So they'll be able to help you out if you go there.
Okay, I will write also. Thank you.
Great. All right. Have a wonderful day, folks.